Okay, before you click stop on the video because it looks too complicated, just wait a second. Let me go ahead and explain all this for you. Okay, this looks complicated, but I'm going to go ahead and explain all this, what it means. What do we have here? I have a line, f of x, and I have a slope that I'm trying to estimate at a. The dy dx, what we're getting into is talk about differentials here. So differentials, in the past, we would have a dy dx come up, and that means the derivative of y with respect to x. Normally we would be treating that as one variable. However, you can actually split apart the dy and dx and treat those as two separate variables. The dy is equal to delta y, or change in y, and your dx is a small change in x, so that's going to be delta x here. So that's the whole idea. So now let's talk about what this means here based on the linearizations that you've already been doing in this section. We have a line here. We're trying to estimate the slope of the line at a. We're going to take another x value, just barely, just slightly, really small. This is an enlarged drawing here, but a little bit further away from a. So that's going to be, the d of x is a little tiny amount that we're going to be adding. So instead of using delta x, we're going to use a dx here in this case. So that's the distance along here, this part of the triangle. Now this part right here is, if you're on the linearization and you're at the a value here, what you're going to be doing is you're trying to see how far you are away on the line from what the original y value was on the graph itself. So if you subtract this part right here, you'll get the L at a plus dx minus the L at a. This is nothing more than a function at this x value minus the function at that x value, so it's kind of the same thing as like a difference quotient in a way. So we're going to work this out over here separately. So we're taking this y value minus this y value, and then this x minus that x. So when you do that, we have this right here. We're going to use our linearization function that we've talked about before in the earlier part of this section. This part right here would be, this section just up to this one would be your L of a plus dx. That's a linearization by using a plus d of x. And then I have minus L of a, that's going to be your f of a here, because we're going to be actually at the y value of the original function. Okay, so that's where that part comes from. Now this is our linearization, and remember, it's x minus a is the formula for your linearization. What's the x value? The x value we're using here is a plus dx. So that's x minus a in the linearization formula. F of a and f of a, they're going to cancel out here. And then when you simplify the part inside the brackets here, the a's cancel and you get d of x. So we're saying that the change in L here is your derivative at a, and then times the little increment amount minus the small little dx that comes afterwards. Now that's all that was talking about your d of x. Now we have the d of y right here is the actual y value on your regular function, a plus d of x and f of a plus d of x. We have that right here, and we can get our delta y is going to be this one right here. So this basically is setting up a picture for you so you can tell the relationship between all of these different variables. Again, your dy and dx are actually considered as separate variables. Change in y is a difference in the y direction. We have our change in x right here. And so again, that's what dy and dx represent. Okay, one more thing. If you're wondering what you're using linearizations for, this picture actually describes it as well. If your d of x is very, very small, then what we're going to say is that this delta L right here, we can represent that as a delta y. We're saying that instead of using the original function, it might be too complicated, we're using a linearization here instead, because again, you're trying, if this is close enough, if this d of x is small enough, that means at this point we're going to get closer and closer and closer, and if you bring that dx all the way down to here, you're going to find that this distance and that distance are going to be very, very close. So remember, this drawing is a kind of expander, blown up version of it. Ideally, you would have these points right next to each other, and that's why we can use a linearization to estimate the actual value on the curve itself. That's pictorially what's happening here.